Okay, today we're going to look at electric potential energy and what that means and how to calculate it. But before we get to that, let's just quickly review the electric field and how the directions work. So we know that if we have a negative charge, our electric field lines go inwards because we're assuming what would happen if we had a positive test charge. So our electric field is inwards, remember, so we based it on a positive. It's going to get attracted, so it'll go inwards, and near the object, you can see our arrows are closer together, so it'll be a stronger electric field, and further away it would be weaker. So then a positive object will have electric field lines that go outwards, because that positive test charge would get repelled or pushed outwards. So that's that. So we also know that what happens if we have one of each. If we put one of each nearby, we're going to get the electric fields sort of interacting with each other. So we know the positive goes outwards, the negative goes inwards, so we're going to get an electric field that goes from one to the other, and then the one that goes outwards at an angle, and this one that goes inwards at an angle, they're going to tend to sort of connect, so we'd end up getting sort of these curvy electric field lines, something like that. And then this one would maybe do something like that, and so on. So we started getting these curves, and then the ones that are out here would maybe curve outwards as well. And probably the only one that would be not curved would be the ones right at the very end. Oops, I got that one the wrong direction. So we'd get sort of electric field lines that look something like that. So that's when we have two opposite charges, the electric fields tend to work together. And what's going to happen is the closer the charges are, the straighter those lines are going to be. So right now I've got them, quite curved in between the two. But if we got the charges super close together, we tend to see that the electric field lines would be a little bit more parallel. So now the idea is, well, how can we create a regular electric field? We don't want it to be where it's bending and different at different levels. We want it to be pretty consistent and uniform throughout. So what we see is that when there's only two charges, we get quite a bit of bending going on. So the idea is, what would happen if we have a whole bunch of charges? So you can see in the diagram here, if we basically set up two plates, so we use two steel plates or whatever kind of metal, and we put one, load it with positive charges, we load the other one with negative charges, we'd see that we pretty much get nice, straight, even electric field lines going from the positive to the negative. The only bends would be right at the very end, so we get sort of this upward and bottom bend here from the positive to the negative. But we can pretty much ignore that, because usually what we'll do is, if we're going to place a charge in there, we would put the charge somewhere in the middle, so then the electric field would be pretty consistent and accurate throughout the whole thing. So this whole idea of using charge plates leads us to electric potential energy. So before we get to that, let's just quickly review what we did with gravitational potential energy, and you'll see that it works almost exactly the same thing. So let's go back to, if we have a ball or an object above ground, we know it's a certain distance above ground, right? So we had some sort of height. We knew that it had maximum potential energy at the top. We just went mgh, and that would be the maximum amount of energy, whatever it would have as potential. Then we know that as it falls, okay, so if it's somewhere down around there, our potential will be a lot less, right? Because it's a less height, so we'd have less potential now. But we know that our kinetic would be gained, right? We went from a zero kinetic at the top to more kinetic as it falls. So it's going to, as it loses potential, it's going to gain kinetic. And then if it was right at ground level, we basically say our potential is 0, and our kinetic now would be max. So all of the energy is converted from potential to kinetic. Okay, so the idea of sort of the energy switching from one to the other as it falls, and then the idea then is, well, what happens if we want to pick up that ball and put it back to where it was? If we lift it back up, we're going against gravity, so we're going to have to do some sort of work or change in energy to be able to move it back up. So the idea is we're going to gain potential as we force it back up again. But our body is applying that energy to lift it back up. Once it's up there, it'll now have potential, and it could do its thing all over again. So now the idea is, what happens if we do the same sort of thing in terms of electric potential energy. So the logic works exactly the same. The only thing that's different, instead of it being a ball above ground, what we're going to do is we're going to think of two plates being separated. So we'll have our positively charged plate there, and let's call our negatively charged plate down here. Okay, and since we typically use a positive for our test point, we're going to use the same logic. So let's suppose we have a test object right at the top. Right, and these don't have to be top and bottom, they could be sideways, whatever, but I want to draw it just like gravity so it looks almost the same. So our positive test point's right at the top plate, so we know at this point then our potential will be maximum. Right, and our kinetic would be 0. Right, so before it moves, right, when we first place it in there, it's going to be up near the positive plate, so it's not moving, it has 0 kinetic, but we know its potential is maximum because of being a positive, it's going to repel from the positive plate and it's going to move towards the negative plate. So we know it's going to, basically, in essence, the way I drew this diagram, it's going to fall. So instead of gravity being the thing that's going to cause it to accelerate, it's going to be the electric field that's going to cause that thing to accelerate. But it works pretty much the same idea. So as we move further and further down, so let's suppose it's somewhere halfway in the middle, we would probably get a potential of being half as much, and our kinetic then would be the other half. And then once we get right to the negative plate, our potential is now 0, and our kinetic would be maximum. So exact same logic as we did for gravity, just the only thing that's different now is it's the electric plates that are causing that object to move. And then once again, if we want to take that charge and force it back up to the top again, we're going to have to do some sort of work or energy to move that, to gain the potential energy back again. How much work is it going to take for us to do that? Well, it's going to depend on what the charge is. So if this was just a small positive charge of, say, 1 coulomb, it's going to take a certain amount of work to do it. But if we made the charge double, we're going to have to push twice as hard. If it was triple, we'd have to push 3 times as hard. So the amount of charge will determine how much work it has to be done. Okay, so the second thing is if our electric field is super strong. So gravity is basically the same all the time. So when we lift up an object, we're pushing that up ball or whatever against gravity. But in this case, depending on how much we charge the plates, the electric field could be really weak, which would be easy to move the charge, or it could be super strong, which we're going to take a lot of work to do. So how strong that is will make a difference. And then also the last one, how far we move it. Right? Just like gravity, if we lift it up a long ways, we're going to have to do a lot of work. Same thing, if our plates are separated a long ways, it's going to be more work than if we only took that charge and had to move it a small distance, right? So if the distance is small, it'll be less energy or work. Distance is large, it's going to be a lot more. So now what we're going to do is introduce a new term and a new formula, and the idea is, what does voltage mean? So we've been talking about electric potential energy, right? The potential energy of that charge to move. Electric potential energy, or sometimes we just call it electric potential. Sometimes we call it electric potential difference or potential difference. So all of these terms can be used interchangeably, and you'll see them, in various forms on different documents. But what we're going to basically call it now is voltage. So if we have a charged plate, and so if you look at a battery that says 9 volts, what that means is between the positive and the negative plates, we have 9 volts of energy in between those plates. So it would take, for example, if we had a positive charge here, and we're going to move that up, it's going to take us 9 volts of energy to be able to do that. So let's figure out what that means in a little bit more detail. So voltage is the change in potential energy per unit charge. So I just said it would take 9 volts of energy. Well, energy is joules. But if this is a 9 volt gap and we have 1 coulomb charge, we would say 9 volts then is equal to 9 joules of energy per that 1 coulomb. So voltage is joules per coulomb is our unit. Okay, so it's just like saying, in terms of gravity, we'd say how much work would I have to do, or how much energy would I have to do to lift something against gravity per kilogram. So if we were lifting up a 1 kilogram object, we'd say we'd have to do 10 10 joules per 1 kilogram to lift it up. So voltage works the same, except it's going to be how much energy per coulomb instead of per kilogram. Our units, you can see here, I wrote it as joules per coulomb, but we use the word volts just to honor Alessandro Volta was his name. He did lots of physics work in electricity, so they named the volt after him. So you just got to remember that a joules per coulomb is the same thing as a volt. Okay, and you can use either or. So let's do a quick, easy example. So it says we got 3.4 coulomb charge, and it says it gains 2.63 joules as it moves through an electric field. So in this case, we don't even really care whether it's positive or negative. We have 3.4 charge, and it says it's moving through an electric field. It doesn't even necessarily have to go from top to bottom. It could be going from middle to anywhere. So basically any distance movement, right, as it moves, its potential energy is going to decrease, its kinetic energy will increase. So whatever the change is going to be how much energy was converted. So you can see in this case it says it gains 2.63 joules, so we'd assume that that would be our kinetic energy, but it really doesn't matter. We just want to treat that as our change in energy. So we got our charge, we got our change in energy, so our voltage then would be 2.6 times 10 to the 3 divided by 3.4, and that gives us 7.6 times 10 to the 2 volts. So joules per coulomb, we'll write it as volts. So the question, the last part of the question is this an increase in potential or increase in kinetic? And it could be either depending on the direction. So in this case, the question says it's moving on its own. So it would be like a positive charge moving towards the negative plate. So if it's moving on its own, we would say an increase in kinetic. If we were pushing that charge, so let's suppose we went the opposite direction. If it started at the bottom plate and we're going to push it upwards, then we're going to move it from zero potential to kinetic. So then that would be an increase in potential energy. So it's the same calculation. You just got to be careful of direction and whether it's going to happen on its own or whether we're going to have to apply energy to make it happen. One last topic, and the idea is sometimes it's not going to be convenient to work with joules just because we're going to be dealing with really small charges, so our answers would be really big in terms of scientific notation. We'd have lots of large negative exponents and things like that. So what scientists have done is we call it the electron volt. An electron volt is a measure of energy that works for small objects like an electron, proton, things like that. So what you got to be careful of is voltage was a joules per coulomb. An electron volt is not measuring voltage, it's actually measuring energy. So it's like a joule. So it's sort of similar to a joule, but we'd say electron volt instead. And the definition is it's the amount of energy required to move one electron through 1 volt. So if we had 1 volt separation, and we have 1 electron moving one direction or the other, that's an electron volt. That's how much energy it's going to take to move 1 electron, 1 volt. So if we actually figure out how much that works out to, we can use our formula we just had, right? Our formula was V equals E over Q. So what we're going to do then is just solve it for energy. So it would be V times Q, or Q times V. We do 1 electron times 1 volt. We know the charge on 1 electron is 1.6 to the negative 19. So we do that times 1 volt, but remember a volt was joule per coulomb. So you can see the coulombs would cancel, so we end up with 1.6 to the negative 19, which is the charge of an electron. So an electron volt is the exact same thing as the charge of an electron, but it's in energy, not coulombs. Okay, so to convert back and forth, that's all you have to do is divide or times by 1.6 to the negative 19. So let's do the second example. We're basically back to the parallel plates that we had in the previous one. So now it says, how many electron volts would you need to move an alpha particle through 760 volts? So if we figure out the energy, and let's do it in electron volts. So our charge is Q, but remember it's an alpha particle, which is 2, has a positive 2 charge, so that'd be the same thing as 2 times 1.6 to the negative 19. Our volts is 760. So we multiply those together, we get 1520 electron volts. Okay, so it's a pretty easy calculation. Just multiply the two and that's it. So if we want to convert that to joules then, we would times that by, so we'd have 1 electron volt equals 1.6 to the negative 19 joules. So if we have 1520 electron volts, you can see that we would just have to times. We'd go 1520 times 1.6 to the negative 19, that would give us how many joules. And if we do that, we just do that quick calculation, we see that this is the same thing as 2.4 to the negative 16. So it's a pretty small amount. That's why we tend to switch to electron volts when we're dealing with really small charges. It just makes the calculations a little bit easier to work with. And that's all for today.